applications of integration and differential equations. We're going to start by discussing applications of integration, the average value, and then we'll go on and discuss differential equations. That's going to be the last topic in our course. Average value, let f of x be a function that's defined on the interval from a to b. The average value of the function f on this interval is defined to be 1 divided by b minus a times the definite integral from a to b of f of x dx. This definition allows us to extend the concept of the arithmetic mean, so that's adding up all, say, exam scores and dividing by number of students, to a function that's defined in a whole range of values, say average velocity, for example, where the time can range from 0 hours to 2 hours. Here's an example of computing the average value of a function. We're going to compute the average of 2x minus 3x squared on the interval from 0 to 3. Here, a is 0, b is 3, and our function, of course, is just this function, 2x minus 3x squared. According to the formula, the average value of the function is 2x minus 3x squared on 0 to 3 is 1 over the upper bound minus the lower bound, so it's 1 over 3 minus 0, times the definite integral from the lower bound, 0, to the upper bound, 3, of the function 2x minus 3x squared dx. 1 over 3 minus 0, of course, is just 1/3. Definite integral is the definite integral from 0 to 3 of 2x minus 3x squared. To compute this, we find an antiderivative of what's in the integrand, 2x minus 3x squared. Its antiderivative, the opposite of the derivative, is x squared minus x cubed. You can check that. If you differentiate x squared minus x cubed, you get 2x minus 3x squared. Plug in 3, we get 3 squared. Plug in 3 again, we get 3 cubed. So 3 squared minus 3 cubed, that's 9, minus 27. 9 minus 27 is negative 18. Plug in 0 to get 0. 0 squared minus 0 cubed is, of course, 0. That means the average value is 1/3 times f of 3, capital F of 3, minus capital F of 0, which is 1/3 times negative 18. 1/3 times 18 is 6, so 1/3 times negative 18 is negative 6. We conclude the average value of the function is negative 6. Average value of the function on the interval from 0 to 3 is negative 6. So this is useful, especially if, say, there are lots of functions whose domains are a range of values from whose domains are a continuum of values from one value, say in this case 0, to another value, in this case 3. You can take on any number in between. So this could be, say, okay, a car is traveling on the freeway. What's its average speed between 0 hours and 3 hours? So notice that's in contrast to the function being a student's test score, because in that case there's a discrete number of students. There's not a continuum for students from 0 to 3. There's only 1 student, 2 students, maybe 3 students, say, in a small class. And then, of course, the average would just be add up all the test scores, divide by 3. But here, f has a value at 0, that has values at 0.1, at any value between 0 and 3, and there's still a way of computing the average using the integral. Differential equations and general solutions defined. So now we're going to get into the topic of differential equations. A differential equation is an equation that relates y prime to x and y. Now this is a first order equation. We're not really going to have time to talk about second order equations, but there are second order equations, and that would just be where we have an equation that would not only include y prime, but also y double prime. Here are some examples of first order differential equations. Y prime is negative 2x, y prime is negative 2y, x times y prime is y minus 1. If you solve each of these equations for y, what you get is a family of functions. That's also called a general solution. So that means there's more than one function that solves this. Notice, just say solving dy dx is negative 2x. That means find a function whose derivative is negative 2x. Well, we've seen that before. That's just the same as anti-differentiating or integrating. We can solve that. We can say, okay, y is equal to negative x squared plus a constant. Now, solving these other two equations will require a slightly different technique called separation of variables, and we'll get to that in about 2 slides later. An important concept in differential equations is called initial conditions. Let's say you know the rate at which the output is changing, y prime, or you know a formula for the rate at which the output is changing, y prime. That is, you know that y satisfies a differential equation, but you also know the initial value of the output at a given input. Y of a is equal to y sub 0, y naught. This is called an initial condition. Y of a is equal to y naught. If y is, say, the distance, and a is, say, the time, that means if we know the position at a given time, and if we know a formula that gives the rate at which the position is changing, that is a formula that gives the velocity, then we can determine a function that will give the position as a function of time. So solving the differential equation subject to y of a is equal to y naught will give only one function, y of x. So in this case, what this means is, let's say, we go back to when Newton first was working and discovering calculus, then he was looking at, okay, planetary motion and trying to predict where planets would be at a later time. You could measure planets at a given time and position of planets at a given time, and also there's a formula from equation of motions that give an equation for the rate at which the planet is changing, rate at which the position of the planet is changing with respect to time. There's an equation, a pattern that rate will satisfy. And solving this differential equation subject to the initial condition will allows astronomers to predict the position of the planet at a later time. So here's an example with a car. Let's say the odometer of a car is broken, but the speedometer is working. So here's a picture of a speedometer. Here's the odometer with an X through, indicating that it's broken. If you look at the speedometer, the driver can determine that the velocity follows a pattern. It is v of t is 50t plus 10. T is the number of hours since the car got on the freeway, and v is the number of miles per hour, the speed of the car at t hours after it got on the freeway. After 1 hour, the driver has passed milepost 27 on the H1 highway in Hawaii. So what this means is that the driver has a formula for the speed of the car as a function of time, and the driver also knows how far the car has traveled on the highway after an hour. The question is, can the driver determine how far the car will be after, say, 2 hours? The answer is yes. The velocity of the car follows the pattern v of t is 50t plus 10 for a full 2 hours. How far will the car have traveled on the freeway after 2 hours? Let's let s of t be the distance the car traveled on the freeway, t hours since entering the freeway. In that case, s prime, the derivative of distance, is going to be velocity. That's always true. Derivative of distance or derivative of position is always going to be velocity. So s prime of t, or ds dt, is equal to 50t plus 10. This here is a differential equation. And we're given the initial condition, s of 1 is 27, because the driver looked at the milepost on the freeway and saw that after 1 hour, the driver had traveled 27 miles on the freeway. It was at milepost 27. Now to find s of t, to find the family of functions that satisfies this differential equation, we're going to save the initial condition for later. We integrate 50t plus 10. S of t, just anti-differentiate 50t plus 10, we get 50 t squared over 2 plus 10t plus a constant. 50 over 2 is 25, so we're left with 25 t squared plus 10t plus c. Now, to find c, we use the initial condition. S of 1 is 27, S of 1 is 25 plus 10 plus c, 35 plus c is 27. That means c is negative 8. Now we have this function. So before s was a family of functions, s of t was 25t squared plus 10t plus c. But now that c was equal to the specific number 8, we only get this one specific function that predicts how far the car will be on the freeway as a function of t hours after entering the freeway. So 25t squared plus 10t minus 8. We're asked to determine the distance the car traveled after 2 hours. So here's what we compute. S of 2 is 25 times 2 squared plus 10 times 2 minus 8. 25 times 4 plus 10 times 2 minus 8. 100. 25 times 4 is 100 plus 2 times 10, which is 20, minus 8. That gives you 120 minus 8, which is 112. We conclude that after 2 hours, the car has traveled 112 miles on the freeway. So notice after 1 hour, it was at milepost 27. After 2 hours, it's going to be at milepost 112. And that's because the car is traveling pretty fast. I mean, its speed is going, after 2 hours, its speed is going up to, it was 50 plus 10, so it's going up to 70 miles an hour. And of course, 70 plus 27, okay, so that's going to be around over 100 miles. Separation of variables. Suppose the differential equation can be rewritten as g of y is dy dx, or g of y dy is f of x dx. This means the variables are separated. dy is separated from dx. We can solve the equation by integrating both sides. We integrate g of y we integrate this side with respect to y. We integrate this side, which you can integral here, with respect to x. This will give capital G of y equals capital f of x plus c, where capital F prime of x is equal to little f of x, and capital G prime of y equals little g of y. Now sometimes this equation can be solved for y. We'll see how that works out in the next example. Let's say there's initially 500 cells of bacteria on a doorknob. When we spray Lysol, the bacteria is going to go away. Lysol is intended to kill germs and bacteria. And it turns out that we can model this by the rate at which the bacteria is decreasing is equal to twice the amount of bacteria remaining. It's an approximation. If we find a formula for the amount of bacteria left after t hours after spraying the Lysol on the doorknob, how do we do this? Well, let's translate that word problem into a math problem. Let P be the amount of bacteria remaining on the doorknob t hours after spraying Lysol. The differential equation P satisfies is dp dt is negative 2p. Right? The rate at which the population of bacteria decreased was equal to 2 times the bacteria remaining. Here we have a negative because the population is decreasing. So dp dt is going to be negative 2 times p. P of 0 is 500. We multiply both sides of dp dt, which is negative 2p, by dt to get the following. dp is equal to negative 2p dt. We divide both sides of dp was equal to negative 2p dt by p to get 1 over p dp, which is negative 2 dt. Okay, so this Here it's separated. It wasn't separating until we got this equation. 1 over p dp, all the p is on one side, and negative 2 dt, all the t is on the other side. Integrate both sides. We integrate 1 over p dp. We integrate negative 2 dt. Antiderivative of 1 over p is ln of p. Now notice p is always positive because population can never be, well, it could be 0, but it could never be negative. So there's no need to put the absolute value here. Antiderivative of negative 2 is negative 2t plus a constant. We can solve this by putting both sides in the power of e. E to the ln of p is p. E to the negative 2t plus c is just negative 2t plus c put in the power of e. Using laws of exponents, you can pull out e to the c. We get e to the c times e to the negative 2t. We're left with a times e to the negative 2t. A is equal to e to the c. We plug in the initial condition to find a. P of 0 is equal to a, which is equal to 500. A is equal to 500. Our conclusion is that the amount of bacteria remaining on the doorknob t hours after spraying Lysol is P of t is 500 times e to the negative 2t. You can check this indeed satisfies P of 0 is 500. And when you differentiate it, you get negative 2 times 500 times e to the negative 2t, which is negative 2 times b. And this is exponential decay, so if you look at a graph of that, that means that the bacteria is initially decreasing at a rapid rate, but then when there's fewer bacteria remaining, it's decreasing at a less rapid rate. Okay, so that's it for today's lecture. This material will be included on your practice final and also your actual final, both of which will be on website.